talk about titrations, and we actually have more than one type of titration, and you probably saw that with your simulation that you could have different things going on. Here is an example of a strong acid that's being titrated with a strong base. And the reason why you know that there's a strong acid is the first thing is when you look at the bottom of the curve at 0 milliliters, you notice that the pH is low. And usually the pH, if it's around 1, we're talking about a strong acid. Now the reason why you know that it's a strong base is when you look at the midsection or the end point of the titration, it actually is close to pH of 7, which is a neutral pH. So you're assuming that all of the acid and all of the base have neutralized each other and you're left with a salt. So that's a clue of how you can tell that you're dealing with a strong acid and a strong base. And the other thing is when you look at the top end of the curve, notice that the pH is hovering around 12, and pH of 12 is a strong base pH. So that's more evidence of that type of curve. Now the easiest thing to do is if you need to figure out how much of the unknown you need to reach the equivalence point, and typically you have all except one of the parts of the solution. So typically they give you the starting volume, the starting concentration, and then they'll give you the molarity of the second solution, and you're solving for the missing volume. So they're assuming that you're trying to figure out how much of the second solution, either acid or base, you would be adding to get to the equivalence point. Okay, now for weak acids, it's a little bit different here, and maybe you noticed when you were doing your simulation. The reason why you have a weak acid is you're actually looking at a pH higher than 1, so it typically is a very higher, or it's not a low pH. The other thing is the way you know that you have a strong base is notice that the pH or the equivalence point is higher than 7. So that typically is a sign that you are dealing with a strong base. And notice that the end point is actually not quite 13, but that is an indicator of what's going on. Now, I'm going to show you in a separate worksheet that when you are doing these kind of calculations, you can't do V1 M1 equals V2 M2. So you actually have to do things like an ICE table. So I'll show you how to do that. The other thing is we're going to go to KW because we want to figure out the dissociation constant or the equilibrium constant for that. If you were to determine the halfway point, and that's essentially where the acid has formed anions. I'm not going to make you do it in this section, but that's essentially what you could use to figure out the equivalence point. All right, here is another graph. So here we have a weak base, and the way we know it's a weak base is when we're starting here, it's less than 12, so it's closer to neutral. And the other thing is the equivalence point, notice that it's below 7. So that tells us that we're dealing with a strong acid. And notice that the final pH is very close to 1. So that is a signal that we're dealing with a strong acid. Now just to show you for rounding out your knowledge, I will not ask you a question like this on the test, but we do have situations where we have diprotic. And notice that diprotic could be, this is oxalic acid or this is our carbonic acid. So they have two hydrogen. And notice that there's two equivalence points because there's two ways, or there's two hydrogen that you can dissociate from that acid. Like I said, I'm not going to ask you a question on the test for that.